we are going to share this screen, and share this. Any screen is visible? Hello?
Yes, sir.
Yes, sir.
Not this one. I wanted this one actually. Right. Okay. Okay, may I start then? Hello? Hello, any screen is visible?
Yes, sir. Yes, sir.
You find here the chapter solution, the colligative properties of the solution. So you understand the effect of temperature on solubility, whereas molality and mole fraction temperature independent. Then the colligative properties, as we have already said, the lowering of the vapor pressure and Raoult's law. Naturally, it will be related to the fractional distillation, the boiling point elevation, and you know the freezing point depression. Then you also know already the determination of the molecular weight by freezing point depression or the boiling point elevation that we have already discussed. Then colligative properties and dissolution of the electrolyte. Okay, so that we will discuss in due course, where you will find the Van 't Hoff factor comes into play, and other than that, you will find the osmotic pressure as well. And these are molality and mole fraction, all this we are not going to discuss. So one thing you understand already, that the colligative properties are the properties of solution that depend solely on the number of particles dissolved in the solution. Number of particles means number of the particles of solute. So colligative properties do not depend on the kinds of particle dissolved, as we have already explained that. Okay, it depends on the number of particles. So colligative properties are a physical properties of the solution. Always remember, these are the not chemical properties, because whenever you are saying the relative lowering of the vapor pressure, boiling point, freezing point related matter, the osmotic pressure, so naturally these are going to be the actually physical properties. So therefore the colligative properties are a physical property of the solution. Okay. Then, as we have already said, the colligative properties of a solution, there are 4 common types of colligative properties. That is vapor pressure lowering, that's we have already explained, the relative lowering of the vapor pressure, freezing point depression, elevation in the boiling point, as well as the osmotic pressure. Then the lowering of the vapor pressure and Raoult's law, already we have explained this. The Raoult's law model this effect in ideal solution. That derivation of the Raoult's law, already we have explained. Suppose the partial pressure of the solvent equal to mole fraction of the solvent and its vapor pressure in pure state. That already we have explained. With the lowering of the vapor pressure, as we have already explained, that derivation we have done. Okay, and therefore, as per of the fractional distillation, you have the idea. As you know, the distillation is a technique used to separate solutions that have 2 or more volatile components with different boiling point. And a simple distillation has a single distillation column. Simple distillation gives reasonable separation, and whereas the fractional distillation gives increased separation because of the increased surface area. Generally, you will find that in any suppose Indian oil, the petroleum, you will find that whenever they are carrying out from the crude petroleum, okay, after to some extent purification, concentration, actually the separating the various types of hydrocarbon on the basis of their different boiling range. That is by actually fractional distillation. Earlier we used to do by bubble cap fractional distillation also. In that case, you will get suppose the petrol or gasoline, diesel, kerosene, like that. Okay. So therefore, you are finding the fractional distillation gives increased separation because of the increased surface area, and commonly glass beads or steel wool are inserted in the distillating column. Then the boiling point elevation, the other day we explained the addition of a non-volatile solute to a solution raises the boiling point of the solvent solution above that of the pure solvent. And this effect is because the solution vapor pressure is lower, as we have already explained by Raoult's law. And the boiling point elevation relationship you will find like this, that is that del TB equal to kBm. As you know, the del TB means the boiling point elevation, M means molar concentration of the solution, and kB, you know, the molar boiling point elevation constant of the solvent. Okay. Then you find the numerical already you have also done. What is the normal boiling point of a 2.50 molar glucose C6H12O6 solution? So as you know, del TB is equal to kBm. As you know, the molar elevation constant for water is 0.512. Okay, Kelvin Kelvin per molality. Okay, so therefore into the molality value 2.50. So m is cancelling. So del TB actually the difference in the boiling point actually, that means del TB means elevation in the boiling point, that is actually the boiling point of the solution minus boiling point in the pure solvent. You know, so what is the difference in degree Celsius? That is going to be the same as difference in Kelvin. So therefore you are finding that is the boiling point elevation is 1.28 degrees Celsius. So boiling point of the solution in degree Celsius is going to be 100 degrees Celsius plus 1.28. So 101.28 degrees Celsius. In terms of the Kelvin, you have to add 273.15 or so. Okay. Then the freezing point depression, as you understand, we have already explained. The addition of a non-volatile solute to a solution lowers the freezing point of the solution relative to the pure solvent. Here you are finding the lowers. That means in earlier you find TB greater than TB0, where TB is the boiling point of the solution and TB0 is the boiling point of the pure solvent. And whereas here you are finding depression in the freezing point, that means here you are finding TF0 minus TF. Okay, and here TF0 is the freezing point of the pure solvent, and whereas TF is the freezing point of the solution. Then you find the same thing, the freezing point depression relationship for freezing point del TF equal to Kf into M, where del TF freezing point depression of the solvent, M means molar concentration of the solution, and Kf means freezing point depression constant for solvent. Okay, so therefore the freezing point depression, you are finding the, you see the similarity of the two relationship for freezing point depression and boiling point elevation. You are finding in case of the freezing point depression, del TF is equal to Kf into M, and del TB is equal to Kb into M. So therefore both del TF and the del TB, you are finding they are colligative properties. Why? Because they actually depend upon the number of particles of the solute, okay, which are being dissolved in the solvent, which are causing this actually, because M is the molality, and M is the molality means the number of moles of solute per kg of the solvent. So fundamentally you are finding the freezing point depression and the boiling point elevation are the same phenomenon. The only difference of the size of the effect, which is reflected in the sizes of the constant, because in case of the Kb you are finding it is 0.52 value, and whereas Kf value is 1.86 for water, for example. Hello, after this it is clear? We are actually the other day we had studied. Hello?
Yes, sir.
Yes, sir.
Okay, fine. Then you are finding the freezing point depression, the same thing, they calculate the freezing point of a 2.50 molar aqueous glucose solution. Look at here. The earlier for the same 2.50 molar aqueous glucose solution, what was the elevation in the boiling point? There we found hardly 1.28 degrees Celsius or so. And here you are finding the depression in the freezing point of the solution is going to be minus 4.65 degrees Celsius. Okay. Why? Because you look at here, the del TF is equal to Kf into M, and here Kf you find the for the value for water actually 1.86 or so. Okay, and then the value of molality you are putting, that is 2.50. Okay, and therefore after calculation you are finding del TF equal to 4.65 degrees Celsius. The del TF means what? That is actually TF0 minus TF, and TF0 that is for pure water is actually 0 degrees Celsius. So therefore 0 degrees Celsius minus 4.65. Okay, so that's why you are getting the freezing point of the solution is going to be minus 4.65 degrees Celsius also. Then determination of the molecular weight by freezing point depression. This side, because the same thing what we explained the other day, del TB is equal to Kb into M. So naturally del TB is equal to Kb into, in place of M you are writing W2 by M2 and divided by W1 by 1000. Similarly, in case of del TF is equal to Kf into M, so there you are writing that in place of M, that is W2 by M2 by W1 by 1000. Okay, So therefore, you find the size of the freezing point depression depends on the two things: the size of the cave for a given solvent, which are well known, and the molar concentration of the solution, which depends on the number of moles of solute and the kg of solvent. Because that's why you are saying that the depression in the freezing point and depression in the boiling point actually directly proportional to the molality of the solution. Okay, from that point of view, that means the number of moles of solute per kg of the solvent. So naturally, these are the colligative properties, which depends upon the actually number of solute particles. It doesn't depend upon the nature of the substance you are actually dissolving. In the sense, actually, suppose you will find for non-electrolyte one kind of colligative properties, for electrolyte the one kind of colligative properties. From that point of view, you can say that what we observe in case of the non-electrolytic substances, adding in terms of the solute, we find the difference in the electrolytic solution, where you are finding that electrolyte means ionic compounds or other you are adding. But however, ultimately it is going to depend upon the how many particles are there in terms of the solute for a given solvent. From that point of view, we are saying ultimately that it is not dependent upon the nature of the non-volatile solute we are adding. Rather, it depends upon the ultimately the particles of the solute, the number of particles of the solute. The more number of the particles of the solute, you will find the more you will find that actually the colligative properties. Okay. Then you look at here, a 30-gram sample of a new covalent compound, a non-electrolyte, was dissolved in 2 into 10 to the power 2 gram of the water. Okay, that means simply 200 gram of the water. The resulting solution flows at 5.58 degrees Celsius. What is the molecular weight of the compound? Hello, this numerical is visible. Hello.
Yes, sir.
Okay. How we can solve? We can solve like this. We can write simply the equation del Tf is equal to Kf into M. Your objective is to find out the molecular weight of the compound. So naturally, what's the del Tf? The resulting solution throws at actually minus 5.58 degrees Celsius. So naturally, you are writing actually that 5.58 degrees Celsius, that is the del Tf. Because project minus 5.58 means what? That means 0 minus 5.58. That means you are finding del Tf actually 5.58 degrees Celsius. And what's the value of Kf? You know, 1.86. So from here you are getting the molality at 3 actually. Now again the molality means you know M equal to, at the very beginning you could have written, or in stepwise also you can write. The molality means you know that is W2 by M2 and divided by W1 by 1000. Okay, the W2 means it is the amount of solute in gram. Here amount of solute means the covalent compound non-electrolyte. So no problem. Okay, and that is actually 37 gram. So naturally you are writing the molality, that is M3 equal to, you are writing 37 divided by M2, that you have to find out, and divided by the 200 by 1000. So naturally you are writing the molality M equal to finally 37 by M2 into 1000 by 200. So 1000 by 200 actually you are writing. Okay, so finally what you are getting that suppose we have said M means 3 into W to 37 by M2 into 1000 by 200. So naturally you can write that M2 equal to, basically capital M2 equal to, you are saying 37 into 1000 and divided by 3 into 200. Okay. Hello, are you getting my point?
Yes, sir.
So in this way, if you calculate, you can find that ultimately the M2, the molar mass is going to be 61.7 gram per mole. So naturally, you just write this numerical and you also simultaneously try to solve it, that whether you are getting the molar mass that is 61.7 gram per mole for the non-volatile compound what you are adding. Okay. Then you will find that so far we have explained the relative lowering of the vapor pressure at the first beginning. Then we have explained elevation in the boiling point. Then we have explained the depression in the freezing point. Okay. And then the another important area is there, that is the osmotic pressure or mean osmosis. That I will come to that. But before that, let us understand the colligative properties and dissociation of electrolyte. Okay. Sometimes you can find that what you are adding the non-volatile solute, they may not remain as simply the molecules the way we are adding. So naturally it is applicable to basically the non-electrolytic substances. But whenever you are adding some electrolytic substances, you know that in aqueous medium they are going to dissociate into ion. So naturally it is expected the colligative properties should actually increase with the electrolytes. And on the other hand, sometimes it may happen depending upon specific solvent that when you are adding some non-volatile solute, they may undergo association, starting from dimer to others. Means the monomer combination dimer for a minimum. So in that case, when the association of the solute molecule takes place, you understand the number of solute particles decrease. So therefore, the colligative properties also decrease. So always you remember, in comparison with the normal, the non-electrolytic substances, as there will be no association or dissociation of those chemical substances when you are adding to the solvent. So in that case, what will be the expected colligative properties? In comparison, whenever you are adding some electrolyte, as you know, electrolyte, they do not remain as free molecules, they actually ionize. So ionize means the number of particles are going to increase. So that's why always you will find by the addition of the electrolyte, the elevation in the boiling point, depression in the freezing point, relative lowering of the vapor pressure, and osmosis of the solution increase. That means overall you are saying all the colligative properties increase. And on the other hand, if the added non-volatile solute, they make association, then what will happen? When the solute molecule associate, the number of solute particles are going to decrease. So in that case, you will expect the colligative properties decrease. So we will explain it one by one. So let us understand this first. Hello, this screen is visible. Hello.
Yes, sir.
And am I audible?
Yes, sir.
Okay, fine. So here you see the electrolytes have larger effect on boiling point elevation and the freezing point depression than non-electrolyte. Very simple. Because for example, at the very beginning itself I explained, suppose you are taking 1 mole of urea solution, 1 mole of the sugar solution. You know the sugar is a covalent compound. Then you know that glucose is a covalent compound. Suppose you know urea is a covalent compound. So they are not going to ionize in the solution. So they remain as the same number of the molecules, okay, as you are adding. But the moment you are adding, suppose NaCl. Now NaCl, what is happening? Suppose if you add 1 mole, then it is producing actually 2 mole of the ion. Because per 1 molecule of the NaCl in aqueous medium, it is dissociating into 1 Na plus ion and 1 Cl minus ion per molecule. So naturally, for 1 mole of NaCl, after dissociation, it is giving you 1 mole of Na plus ion and 1 mole of Cl minus ion. So naturally, you can expect that their colligative properties are going to be double. Okay. So therefore, if somebody asks you that 1 mole of sugar and 1 mole of glucose, 1 mole of urea, and 1 mole of NaCl solution, what will be your observation in terms of the colligative property? So first of all, you already know the colligative properties, which are the actually characteristics properties of the solvent. That is actually relative lowering of the vapor pressure, elevation in the boiling point, depression in the freezing point, and osmosis of the solution by adding some non-volatile solute. Okay, this happen. And here you can find these colligative properties actually depend upon the number of particles of the solute are being added. So from that point of view, whenever you are saying 1 mole sugar solution, you know that is going to be the 1 mole particles. 1 mole urea solution, that is also going to be 1 mole particle. Actually, solution means here aqueous solution. That means you are finding the colligative properties of the water solvent by adding some non-volatile solute. So what is happening? So here you are finding that 1 mole of sugar solution means 1 mole of sugar C12H22O11 in water solvent. Then 1 mole of the glucose, you know the C6H12O6 in actually in water solvent. then you are finding 1 mole of actually the in terms of the molality you are saying, then per liter ultimately, then 1 mole of the urea solution, that also you are saying the 1 mole of urea actually in terms of the number of particles, number of urea molecules in the same amount of the water. But the moment, so therefore in all these cases, with respect to 1 mole of sugar solution, 1 mole of urea solution, and 1 mole of glucose solution, in all these cases, you are finding the colligative properties of the solvent, means here water is going to be same, are not going to vary. Okay, because the number of particles of the solute are going to be same. From that point of view, though it may be urea, though it may be sugar, though it may be glucose, but the moment you are saying 1 mole of NaCl solution, you know the NaCl solution cannot remain as molecules in aqueous medium. And what is happening, as per molecule of NaCl, it is dissociating into Na plus and Cl minus ion. So naturally, per mole of NaCl, after dissociation, it is giving you 1 mole of Na plus ion and 1 mole of Cl minus. So that means you are getting 2 mole of particles. So therefore, what's the colligative properties you observe in case of 1 molar urea solution, 1 molar sugar solution, and the 1 molar actually glucose solution? You are finding the colligative properties are going to be double with 1 molar NaCl solution. So therefore, here you are observing abnormal colligative property. Normally, generally abnormal colligative properties you can find with the electrolyte, where you are finding the what is the expected colligative properties. The in case of the abnormal colligative property you are finding, it is going to be higher in case of the electrolyte. But when on the other hand, when you find the association of the solute molecule takes place, then there also you will observe the abnormal colligative properties. But as the association of the solid molecule takes place, so naturally number of solid particles decrease. So therefore, in that case, you will find the colligative properties are going to decrease than your expected value also. So you just see here, the electrolytes have larger effect on boiling point elevation and freezing point depression than non-electrolyte. This is because the number of particles released in solution is greater for electrolyte. So 1 mole of NaCl dissolved in water to produce 2 moles of aqueous ion, 1 mole of Na plus and 1 mole of Cl minus ion. Okay, and colligative properties and dissociation of the electrolyte, you can find the Van 't Hoff factor, symbol I. The Van 't Hoff actually after the name of scientist Van 't Hoff, who work on this. We represent generally symbol I. If they used to introduce this effect in the calculation, generally I Van 't Hoff factor means you will find basically the observed colligative property and divided by, you will find that is the theoretical colligative properties or the expected colligative property. So observed colligative property in case of the electrolyte, you will find that is going to be actually greater than the expected value. So that's why when you will find for non-electrolyte solute, when there is no dissociation, no association, you are considering ideal condition. In that case, Van 't Hoff factor I is equal to 1. But the moment you are finding that for electrolytes, actually the Van 't Hoff factor I is always going to be greater than 1, because the Van 't Hoff factor I means it is the ratio of observed colligative property or experimental colligative property to the, you will find that is the theoretical or expected colligative properties. So as you are observing with the electrolyte, the colligative property increase, so naturally Van 't Hoff factor is always going to be I greater than 1. And on the other hand, when you are finding the association of the solid molecule takes place, so naturally the number of particles decrease. So therefore, your observed colligative property is going to be less than the expected or theoretical colligative properties. So in that case, I is going to be less than 1. So always remember, under ideal condition, when no dissociation, no association of the solid molecule takes place, you are finding the I equal to 1. And whereas when the dissociation of solid molecules is taking place, you are saying I greater than 1. And on the other hand, when the association of the solid molecule is taking place, you are finding I is less than 1. Hello, it is clear?
Yes, sir.
Okay, fine. Look at here, colligative properties and dissociation of the electrolyte. Suppose if you other than, suppose if we consider here 100% dissociation, provided if we consider it is 100% dissociation, then I has an ideal value of 2 for 1:1 electrolyte, because NaCl, you know, Na plus Cl minus, Ki K plus I minus, LiBr Li plus Br minus. Okay, provided, because you are getting 2 ions per formula unit, provided here you are finding that degree of dissociation is 100% dissociation. Similarly, I has a value of 3 for 2:1, like K2SO4. You are finding 2 K plus and 1 SO4, 2 minus charge. So naturally, you are finding 2 potassium ion and 1 sulfate ion per formula unit. Similarly, KCaCl2, you are finding per formula unit 1 calcium ion and 2 chloride ion. So naturally here you are finding I should have the ideal value 3, because 2 plus 1, 3 mole of ions you are getting. So 3 ions per formula unit, provided in all these cases you are expecting the 100% dissociation is taking place. So that's why we are going to correlate the degree of dissociation with a Van 't Hoff factor, and similarly the degree of association with the Van 't Hoff factor. I would like to tell you, when if you consider the alpha is the degree of dissociation, then you will find the, for dissociation actually the alpha equal to that, you will find I minus 1 by n minus 1. Alpha equal to what you will find? I minus 1 by n minus 1, where alpha represents the degree of dissociation, I represent the Van 't Hoff factor, and n actually represent the how many moles of ions are formed. N represent the number of moles of ion per formula unit. Okay, then you will find for association the formula is going to be alpha equal to that 1 minus actually you can say I minus 1 by 1 by n minus 1, when the association of the solid molecule is taking place. Again, I am saying the alpha equal to, you are saying I minus 1 divided by 1 by n minus 1, where I is the Van 't Hoff factor, alpha is degree of association, and n represents the how many molecules associate per formula unit. Look at here. আচ্ছা এখানে এটা বলেনি অসমোটিক প্রেসার, ওকে হ্যাঁ আমার ওটা ঠিক আছে, আপাতত এটা দেখো তারপর আমি বলছি। Hello, up to this it is understandable?
Yes, sir.
Okay, with another slide I will explain. Now the another colligative property, that is the osmotic pressure. You know the osmosis is the net flow of a solvent. Suppose two solutions are separated by a semi-permeable membrane. Then what will happen? You will find from both the solution, for example, that there will be the flow of solvent, and rather you will find that there will be the flow of liquid from high concentration, from low concentration to high concentration through the same thing, net flow of a solvent. Because when suppose two solutions are separated by a semi-permeable membrane, it is quite possible the solvent across the membrane it may flow whether from the higher concentration to lower concentration or from lower concentration to higher concentration. But as you understand that the high concentration means the where the amount of solute is more and the solvent is less, and whereas low concentration means where you are finding the amount of solute is less and amount of solvent is more. So therefore, from low concentration solution, there will be net flow of solvent to the high concentration of the solution, unless and until the concentration of the both the solution become same. That phenomenon is known as osmosis. And whenever there is a flow of solvent from low concentration to high concentration and osmosis is taking place, then on the high concentration side, if you apply some pressure to prevent that osmosis, that is known as osmotic pressure. Let's understand this. Suppose osmosis is the net flow of a solvent between two solutions separated by a semi-permeable membrane. The solvent passes from the lower concentration solution into the higher concentration solution. Example of semi-permeable membrane include cellophane and saran wrap, skin, cell membrane, like that. Look at here. Hello, this slide is visible. Hello?
Yes, sir.
Okay,
Yes,
fine.
sir.
This slide is visible. Okay, fine. Just a moment. Ogni has joined. Okay, no problem. Ogni joined, Deborina, or no, Asina. So, um, Mrityunjay, have you joined? And then, all good. Okay, fine. So let us continue where we are continuing. Now the screen is visible. Hello?
Yes, sir.
Okay, fine. Look at here. Suppose that there is a semi-permeable membrane which separate its solution from the solvent. So as you understand, between solution and solvent, the solvent has the low concentration and solution has the high concentration. So therefore, the net flow of the solvent is taking place from the low concentration solvent to the solution, and that phenomenon is known as osmosis. And then to stop that osmosis, actually, okay, to maintain that, you are applying the pressure on the solution side to stop, to prevent the osmosis. So naturally, how much pressure you are applying to prevent that osmosis, that is known as actually osmotic pressure. And that's why you find the cause of reverse osmosis. By reverse osmosis, generally we purify, we actually remove the total dissolved salt from the solution, okay, to get the purified water. Okay, now, so generally osmotic pressure we can represent by pi. Okay, and generally you will find that, as you know, for ideal gas, if you remember, the equation is what? PV equal to nRT, if you remember, for n moles of an ideal gas, where P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature. Then you find the P equal to N by V at T. So you are saying P equal to N by V means molar concentration. Either you can represent by capital M, or you can represent by C at T. Okay, so you can say P equal to C at T for ideal gas. And as far as the ideal solution, you will find it behaves like an ideal gas. At the very beginning I said, so naturally the osmotic pressure, you will find the relationship that is nothing but pi equal to C at T, where pi represents, in place of P, osmotic pressure, C is the molar concentration of the solution, R is the universal gas constant, and T is the absolute temperature in Kelvin. Okay, and however, again, by Van Top, actually you will find, just in case of the ideal gas equation, with respect to the Boyle's law, with respect to the Charles law, we generally try to understand or define. The same way we can understand these also. You just see osmotic pressure, you are finding pi equal to m at T. So that means pi means osmotic pressure in atmosphere, m means molar concentration of the solution, R means the universal gas constant. Suppose here it is mentioned 0.08 to liter atmosphere Kelvin inverse mole inverse, and T is the absolute temperature. And sometimes in place of m, that is the molarity represent, you can represent also by C, and C is nothing but, normally you will expect the molar concentration. And in this case, I also would like to mention that for very dilute solution, what will be the molality? The same as molarity. Okay, so for very dilute solution, always you will see the molality and molarity are nearly the same. But otherwise, you know, the molality means number of moles of kg, number of moles of solute per kg of the solvent, whereas molarity means number of moles of solute per 1 liter of the solution. Look at it. For very dilute solution, aqueous solution, molarity and molality are nearly equal. I would like to remind you that generally molarity we represent by capital M, and whereas molality we represent by small m. So therefore you are finding pi equal to, in place of molarity, we are writing molality small m at T. So for very dilute aqueous solution only. So therefore, osmotic pressure measurement also can be used to determine the molar mass of very large molecules such as polymers, protein, and ribonucleotides. So therefore, you are finding from the colligative properties, we can determine that as we started at the very beginning, that from the relative lowering of the vapor pressure, then elevation in the boiling point, then depression in the freezing point, then from the osmotic pressure, we can find out the molar mass of non-volatile solute. Okay, then again I would like to tell you, normally whenever you are writing the equation, for example the relative lowering of the vapor pressure, if you remember that del P, actually if you remember, that was actually del P by P0 x2, or you can say del P equal to P0 x2, if you remember. Okay, that is also the House law. X2 means that is the mole fraction of the solute. Then you can write actually in all these cases that you use the I, small I Van't-Hoff factor. Then the formula, working formula are going to be from relative lowering of the vapor pressure. You can write del P equal to small I, then P0 x2. In case of the elevation in the boiling point, you are writing del TB equal to I KB M. M means small m, molality. Similarly, in case of the freezing point depression, you are writing del TF equal to I KF small m. Then similarly, for osmotic pressure, you are writing pi equal to small I C RT. Okay. Now, for ideal solution, when no association, no dissociation, you will find I equal to 1. Other than that, for electrolytic solution, I is going to be greater than 1. And for when the association of the solute molecules are taking place, we will find I is going to be less than 1. Okay. And you will find also, I will also show you the relation actually that when alpha is the degree of dissociation, then you will find that alpha equal to I minus 1 by n minus 1 for dissociation, where I is the Van't-Hoff factor, alpha is the degree of dissociation, and n is the number of molecules actually dissociate into ions. And on the other hand, when you are finding, or the number of dissociated molecules, I will show you actually by example. And then you can find the, for the association of the solid molecules, you will see that is going to be basically alpha equal to I minus 1 by n minus 1, where alpha degree of association, I is the Van't-Hoff factor, and n is actually number of molecules associate. Okay. Hello, up to this it is clear? Hello?
Yes, sir.
Okay, fine. So here you can find the solution and colligative properties. All these already we have explained, Henry's law also. Okay. Then the methods of expressing concentration of the solution. All these we have completed. So that's why today I took this opportunity. I have taken this opportunity just to round it up. Okay, that is very important. But still, so many things are to be explained, so that I am trying to do the fine tuning. Okay, let us see. These already we have explained. Okay, concept of solubility, saturated solution. Then the solubility, effect of temperature on solubility. That also we have explained. Variation of solubility with temperature for some ionic compound, exceptional behavior, all these effect of change in temperature, all this we have already explained. This is actually solid solution, it means for alloy. That is not required in this case. Here you are studying solution in that. Then the colligative properties, the four colligative properties, the relative lowering of the vapor pressure, okay, concept we have already explained. Then you are finding all these actually the example experiment that you have already studied. Okay, del P by P01, where del P means P10 minus P, that is relative lowering of the vapor pressure, that you are finding in terms of the mole fraction. Ultimately, you are finding the ideal solution, that also you have explained this. Okay, for non-ideal solution, as we have already explained, del A is mixture not equal to 0, del B mixture not equal to 0, and when you are finding the positive deviation, PA greater than PA0 XA, PB greater than PB0 XP, like this, where del H mixture greater than 0, del B mixture greater than 0. Here actually you will find the minimum boiling point isotope. Suppose ethanol, water, carbon disulfide, acetone, carbon tetrachloride, benzene, carbon tetrachloride, toluene, ethanol, cyclohexane, carbon tetrachloride, chloroform, this type of solution. Okay, and then another non-ideal solution here, negative deviation, where you are finding Pa less than Pa0 XA, Pb less than Pb0 XB. Here you will find del H of the mixture less than actually del H mixture less than 0, del V mixture less than 0. Here you will find negative deviation, and therefore you are finding Here you will find the maximum boiling point azeotrope, like that. Example, suppose chloroform, acetone, chloroform, benzene, like this. The azeotrope mixture, as we have already said, the azeotrope mixture I would like to explain further. The earlier I said to that was only to some extent. Whether this screen is visible? Hello?
Yes,
Yes,
sir.
sir.
Okay, look at here. As far as the azeotrope mixture, you are finding a mixture of two liquid which boils at a particular temperature like a pure liquid and distills over in the same composition is known as constant boiling and mixture. These are formed by the non-ideal solution. So always you will find the minimum boiling point azeotrope means here you are finding actually the positive deviation from the Raoult's law, where you are finding Pa greater than Pa0 Xa and Pv greater than Pv0 Xp, and where you are finding del H of the mixture greater than 0 and del V of the mixture is greater than 0. There you are finding minimum boiling azeotrope. And on the other hand, the maximum boiling point azeotrope you will find from the negative deviation from the Raoult's law. That means in that case, Pa is going to be less than Pa0Xa and Pv is going to be less than Pv0Xb. And there you will find that del H of the mixture is going to be less than 0 and del V of the mixture is going to be less than 0. Okay, these are the very, very important from competitive exam point of view, I can say, because we are not sure even you would be able to appear for the board exam. So at least you have to prepare for your competitive exam point of view. Okay, so now, so here you will see the maximum boiling point azeotrope with the non-ideal solution in case of the negative deviation from Raoult's law. Okay, so here you find that the minimum boiling azeotrope, suppose ethanol 95% and water 4.43%. That is by mass. You are finding nearly 95% ethanol and 5% water. Always you will find constant composition. Okay, at the when you are carrying out the distillation, that mixture is known as azeotrope mixture. And whereas the maximum boiling azeotrope you are finding observed in case of the water and HCl. That means water you are finding nearly 20% and HCl here nearly 80% or so. Okay, so like that. And the colligative properties already we have said that from Latin CO means together and ligand means to bind. So colligative property are those properties which depends upon the number of solute particles in a solution irrespective of the nature. These already you have explained. You know that. If I'm not, all this you know. All this you know. Already you have explained. These also you have explained. You know that. Okay. Then again we explain this. If you remember, the Kb equal to MA Tv0 square by del Hv and Kf equal to MA Tf0 square by del Hf. If you remember, Tv0 means boiling point of the solvent, Tf0 means freezing point of the solvent, and del Hf means molar enthalpy of the fusion, and del Hv means molar enthalpy of the vaporization. Or MA means actually molar mass you are finding. Okay, that means you are finding that of the. Hello, are you getting my point?
Sir.
Okay, good. Then osmosis already we have explained like this. Definition of osmosis already you know. Osmotic pressure as we have already explained. The pi equal to, as you have already said. Then here you will find hypertonic solution, hypotonic solution, isotonic solution. I would like to tell you, isotonic solution means same osmotic pressure whenever you are considering between the two solutions. Suppose solution 1 and solution 2. And suppose solution 1 osmotic pressure is pi 1 and solution 2 osmotic pressure is suppose pi 2. So for isotonic solution, pi 1 equal to pi 2. So now from the formula, pi 1 means you can write C1 RT and pi 2 means C2 RT. So now RT cancelling. So you are finding C1 equal to C2. Okay, so therefore isotonic solution means same osmotic pressure and their same molar concentration. And not only that, the molar concentration means you are saying moles per liter. So naturally you are finding in terms of number of moles are also going to be same in both the cases. So therefore isotonic solution, you will find two solutions are called isotonic if they exert the same osmotic pressure and this solution have same molar concentration. Okay, so therefore 0.91% solution of pure NaCl is isotonic with human and the RBCs. Okay, And whereas hypertonic solution means the solution which is having higher osmotic pressure than the other solution. And hypotonic solution means a solution which is having the less osmotic pressure than the other solution. Suppose if pi 1 greater than pi 2, then you will say the pi 1 is hypertonic solution, and whereas pi 2 is going to be hypotonic solution, like that. The reverse osmosis we have already explained. Then the abnormal molecular mass already we have said. Okay, osmosis, like the laws of osmotic. Already I have said the state of Van der factor, Boyle's law, and the mathematical representation. As you know, the pi directly proportional to C. That means C means N by V. Then the state Van der Boyle's law and math empirical expression. Then pi directly proportional to P. So earlier one you are finding in terms of the Boyle's law, and next one you are finding in terms of the Charles law. So finally you are finding that pi equal to CRT. And the Van der factor already we have explained. The I equal to observed value of the colligative property, okay, and divided by the calculated value of colligative property. And then you can say I equal to the normal molecular mass by observed molecular mass. Just opposite, because you are finding the Van der factor is directly proportional to the colligative property, but the Van der factor is actually inversely proportional to your finding the observed molecular mass. So therefore, when I is the number of particles after association or dissociation, the number of particles initially, and so to correct the observed value of molar mass, Van der factor must be included in different expression for colligative property, as I already explained. The del T is equal to I kb m, del T is equal to I kf m, pi equal to I CRT, and del P equal to I PA0 xp. Okay. Now for ideal solution, you will find always I equal to 1. As I have already explained, degree of dissociation, you find here that alpha equal to I minus 1 by n minus 1, okay, where you are finding that what you are finding is one molecule of substance get dissociated into n particles. So that means you are getting the n means the number of particles after dissociation. And where you are finding the degree of association, you are finding alpha equal to I minus 1 by 1 by n minus 1. So in case of the degree of dissociation, you are finding n means number of dissociated ions or number of simply dissociated particles. And whereas here in case of the degree of association, n means the number of particles associate. Okay. So therefore you are already have mentioned the Van der factor I greater than 1 for electrolytic solution. That means for solute undergo dissociation. And whereas Van der factor less than 1 when the association of the solute molecules are taking place. Already we have explained this. Okay. This is overall like that. Hello? Understandable to some extent?
Yes, sir. Yes, sir.
All these we have explained. Just a moment. আমি একটু এনসিআরটির এটা তোমাদের দেখে প্লে করে দেবো। এগুলো অলরেডি আমরা বলেছি, সেম থিং অ্যাকচুয়ালি। এগুলো আমি এক্সপ্রেস করেছি, ওইটাই অন্য আরেকটা এসে সেম থিং, রাইট। These are already explained. The same thing. Abnormal molecular, Van der factor, all these we have already explained. The same thing. Okay, fine. একটু জাস্ট ওয়েট করো, দাঁড়াও। আমি একটু তাহলে কি করতে পারি, তোমাদের আরেকটু আমি এনসিআরটি বইয়ের থেকে রেসপেক্টে তোমাদের একটুখানি ঢালিয়ে দিতে পারি। যারা এক মিনিট আরেকটু ওয়েট করো, জাস্ট আমি একবার দেখে নিই এনসিআরটি এটা একটু দেখে নিই। দাঁড়াও এক মিনিট। এনসিআরটি এটা আছে কিখানে একবার দাঁড়াও এখানে। Solution NCRT, right? Just a moment. screen. Now any screen is visible? Hello?
Yes, sir.
Okay, fine. Just a moment. So here what I want to show you that একটু তোমরা ওয়েট করো, আমি দেখে নিব। জাস্ট a minute. এটা একটুখানি ডিস্টার্ব করছিল। Okay, fine. Now you are the জিনিসটাকে, right? This এই স্ক্রিনটা ভিজিবল তো না? হ্যালো?
হ্যাঁ স্যার।
হ্যাঁ, এটা এনসিআরটির, আমি মোটামুটি করে বলে দিয়েছি জিনিসটা। আমি শুধু ওই জায়গাটা কমপ্লিট করেছিলাম বলে ওই জায়গাটা একটুখানি বলে দেবো, আর দেখে নেবো এখানে ওদের আর কি ফিচার দেওয়া রয়েছে। দাও। If you remember, the other day we explained this one, or actually from here, and there I said the relationship that is here. Look at here. We said that KB equal to R into, you are finding TB square, R into M into TB square, actually TB0 square. That means and 100 into del H vaporization. So means 1000 into del H vaporization actually. 100 is possible. That is in the different way you have to explain. And whereas K is equal to R into TF0 square M1 by 1000 into del H fusion. So here you understand that R and M stands for the gas constant and the molar mass of the solvent, as we have already said, the molar mass of the solvent. And whereas actually you can represent rather that TF0 means it would have been better actually to show. TF0 means actually, don't get confused, it should be TF0 actually. That means it is the freezing point of the pure solvent. Similarly, TB0 square, it is the actually boiling point of the pure solvent, because otherwise TF and TB denotes basically the freezing point of the solution and the boiling point of the solution respectively. That I wanted to show you actually. Okay, nothing else. And as you find, the M1 is the molar mass of the solvent, or is the universal gas constant, and then you are finding 1000. And in case of the KB, you are finding del H of the vaporization, and whereas KF, you are finding del H means it is the enthalpy of the fusion, like that. Okay. Then the remaining things we have already explained. This one, all these we have already explained. This is the osmosis. As you find, the pi equal to CRT. So osmotic pressure is proportional to the molarity of the solution at a given temperature. Just exactly the ideal solution, and that is same as ideal gas law. Then the numerical you have to do. Then the reverse osmosis, as we have already explained. Reverse osmosis means just opposite, where in the osmosis you are finding from low concentration to the high concentration solvent flows, unless and until through a semi-permeable membrane, unless and until both the concentration are going to be same. So that's why you apply pressure on the high concentration side, okay, just to prevent the osmosis. And now when you are applying that pressure more than the osmotic pressure, then what will happen? The reverse osmosis will take place. So in that case, there will be the flow of the solvent from the high concentration to low concentration. That means here, what's the dissolved salt which will be left in the high concentration part, and where the pure solvent, that means water, normally we expect in case of the reverse osmosis of the water from water purification point of view, that will pass through semi-permeable membrane from high concentration to low concentration. So that way you are removing actually the total dissolved salt from the concentrated water, or which is not purified water, from where you are actually removing or separating out the total dissolved salt or solid. So that's why you are finding The direction of the osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side, and that is now the pure solvent flows out of the solution through the semi-permeable membrane, and this phenomenon is called reverse osmosis and is of the great practical utility. The reverse osmosis is used for the desalination of the seawater. Desalination means removal of the salt. Okay, and a schematic setup is there. Okay. Then abnormal molar mass, as we have already explained. Suppose in case of the acidic ethanoic acid, acetic acid, when you are dissolving in the benzene solvent, generally these acetic molecules or the ethanoic molecules will associate. So what you will find here, you will find the expected colligative properties. What is your expected colligative properties? The observed colligative properties is going to be half, because association of the molecule is taking place. Of what? Of acetic acid molecules or ethanoic acid molecules in the benzene solvent. On the other hand, whenever you are finding that the colligative properties is becoming half, okay, then you are finding the molar mass is going to be abnormally high. It is going to be double because it is forming the dimer. So therefore, you are finding the expected, what will be the molar mass? Your observed molar mass is going to be double. And on the other hand, what will be your expected colligative properties? The observed colligative properties is going to be half. Okay, and whereas in case of you are finding the for electrolytic solution, you will see just opposite. Their colligative properties is going to be higher, and whereas the molar mass is going to be lower. Okay, so that's why you are finding this relation. You should remember the I equal to normal molar mass by abnormal molar mass, and that is equal to actually observe, just opposite, observe colligative property by calculated colligative properties. And whereas normal molar mass means here you are saying calculated molar mass divided by abnormal molar mass means where you are finding observed molar mass. So that means you are finding the colligative properties and the Van 't Hoff factor is going to be somewhat directly proportional. Okay, but with the molar mass it is going to be inversely proportional. Okay, and therefore I equal to, you are saying, total number of moles of particle after association or dissociation and divided by number of moles of particles before association or dissociation. And that's the way you can write all this. Already we have explained that. And you will find a lot of numerical based on this. I think this is going to be end, and then the summary. Hello, after this it is clear? Hello?
Yes, sir.
Okay, very good, very good, very good. Then at least one numerical we should do today. Okay, before we finish the class, at least one numerical. Just a moment. Which one I can take? Let's see from the this. Oh, here answer is given. Answer to some in-text question. In-text question 2.1, 2.2. Watch. Open to the in-text question 2.1, 2.2. Let's see. Determine the আচ্ছা হ্যালো 2.40 টা দেখতে পাচ্ছ? আমি একটুখানি করছি, জুম করছি, দেখো তো 2.40 টা দেখতে পাচ্ছ কিনা দেখো তো।
হ্যাঁ স্যার দেখতে পাচ্ছি।
ওকে, ব্যাস এই নিউমেরিক্যালটা সলভ করার চেষ্টা করো তো।
40 টা
2.40 টা, হ্যাঁ
ঠিক আছে।
হ্যাঁ 40 টা 40 টা। আমি তোমাদের শুধু একটা হিন্ট দিচ্ছি, তুমি লিখে ফেলতে পারো যে পাই ইকুয়াল টু small I CRT, where pi is the osmotic pressure, small I টা Van 't Hoff factor that is given here, আর C হচ্ছে molar concentration, R টা হচ্ছে universal gas constant, আর T টা হচ্ছে absolute temperature in Kelvin. আমি আবার রিলেশনটা বলছি, you write pi equal to I CRT, always I টা small I দেবে, pi equal to I CRT, where pi represent osmotic pressure, I represent Van 't Hoff factor, C represent molar concentration, R represent universal gas constant, and T represent temperature in Kelvin. এখানে যখন কোনো ডিগ্রি অফ ডিসোসিয়েশন বলেনি, তাহলে এখানে পুরোপুরি এই ভ্যান্ট অফ ফ্যাক্টর আইটা ধরে নেবে, কারণ এখানে ভ্যান্ট অফ ফ্যাক্টর আইটা বলে দিয়েছে 2.47। আদারওয়াইজ তুমি লক্ষ্য করো, যদি CaCl2 তুমি যদি কনসিডার করতে যে 100% ডিসোসিয়েশন, তাহলে আইডিয়ালি আমার ভ্যান্ট অফ ফ্যাক্টরটা কিন্তু 3 হতো, কারণ পার মলিকুল অফ দ্য ক্যালসিয়াম ক্লোরাইড you are finding 1 calcium ion and 2 chloride ion, so it would have been ideally 3. But however, here you are finding degree of dissociation is not 100%. That's why they are showing I equal to 2.47. Okay, এটা বুঝতে পেরেছো জিনিসটা কি? Determine the amount of calcium chloride dissolved in 2.5 liter of the water such that its osmotic pressure is 0.75 atm. তাহলে এখানে অসমোটিক প্রেসারটা যেহেতু 0.75 atm বলছে, তাহলে তুমি কোন আর এর ভ্যালুটা নেবে? তুমি আর এর ভ্যালুটা নেবে 0.082. you will take the value of R 0.082 liter atmosphere Kelvin inverse mole inverse. And what's the value of capital T? That is equal to 273 plus 27, 300 Kelvin. So capital T equal to 273 plus 27, 300 Kelvin. ঠিক আছে, তাহলে তুমি প্রথমে ফর্মুলাটা লিখবে পাই ইকুয়াল টু ICRT, তারপরে ভ্যালুগুলো লেখো, মানে ডেটাগুলো আগে লেখো, যে পাই ইকুয়াল টু 0. given পাই ইকুয়াল টু 0.75 atm, then you write capital R universal gas constant equal to 0.082 liter atmosphere Kelvin inverse mole inverse, then capital T equal to you write 273 plus 27, 300 Kelvin, আর এখানে তুমি লিখে রাখো ভলিউম ইকুয়াল টু 2.5 লিটার। ঠিক আছে, এবার তুমি যেটা করছো, তাহলে পাই ইকুয়াল টু CRT, তাহলে সি এর জায়গায় লিখবে N/V। তাহলে এখান থেকে তুমি কি হয়ে যাচ্ছে, তুমি পাইটা 0.75 পুট করে দাও, ইকুয়াল টু এনটা তুমি ফাইন্ড আউট করছো, বাই ডিভাইডেড বাই ভি মিন ভলিউমটা কত 2.5। ওকে, ধরে নিতে পারো, কোনো অসুবিধা কিছু নেই, এটা খুব ডাইলুট সলিউশন, 2.5 লিটার অফ ওয়াটার বলেছে, সেটাকে তুমি ধরে নাও, কোনো অসুবিধা কিছু নেই। অ্যান্ড আরটা কত 0.082 অ্যান্ড টিটা কত 300। এখান থেকে তুমি যে মোলসটা পাবে, যে ভ্যালুটা পাবে, সেটা মানে কি অ্যাকচুয়ালি W/M। এবার তোমাকে ডব্লিউটা ডিটারমাইন করতে হবে। হ্যালো, বলো।
3.42 বেরোচ্ছে।
3.42 কি বেরোচ্ছে? অ্যামাউন্টটা, তাই তো?
একদম লাস্টে, হ্যাঁ, গ্রাম।
হ্যাঁ, এটা তুই কিভাবে বার করছো? কারণ তুমি এনটা পেয়ে গেছো।
হ্যাঁ স্যার, এনটা তো দেয়া আছে।
পেয়েছো এনটা কত পেয়েছো?
0.031।
0.031
মোল।
0.031 হলে এই ক্যালসিয়াম ক্লোরাইড কত হচ্ছে? ক্যালসিয়াম মানে 111 ইনটু 0.
হ্যাঁ, ওটা করলে বেরোচ্ছে 3.42।
1 মোল মানে কত? 111, তাহলে 0.03 হ্যাঁ মোল পাচ্ছো, তাহলে সেইভাবে তুমি করতে হবে। বুঝতে পেরেছো?
হ্যাঁ
এটাই
স্যার।
আছে, that is the way one have to solve. Hello, whether everyone you have understood? Anybody is having any doubt whatsoever? তাহলে আমরা দেখো সলিউশনটা আজকে রাউন্ড আপ করে দিলাম। তোমাদের কাজ হচ্ছে তোমরা কিছু নিউমেরিক্যাল সলভ করে আমাকে অবশ্যই পাঠাবে। আমি একটা গ্লান্স করে নেবো যাতে আমার বুঝতে সুবিধা হয় যে তোমরা জিনিসটা ফলো করেছো। পেন্ডিং রেখে দেবে না।
আমারও 3.42 এসেছে, 3.42 গ্রাম।
বাহ, ঠিক আছে, তাই হবে। যা মোলস আসবে সেটাকে তুমি 1 মোল মানে এখানে দেখলে 111, সেটাকে দিয়ে মাল্টিপ্লাই করলেই ওই অ্যামাউন্ট অফ দা ক্যালসিয়াম ক্লোরাইডটা পেয়ে যাবে। ঠিক আছে, আমরা ইনফ্যাক্ট প্রত্যেকটা টাইপও করে নিয়েছি, একটা করে নিউমেরিক্যাল, একটা রিলেটিভ লোয়ারিং অফ দ্য ভেপর থেকে করেছি, এলিভেশন ইন দ্য বয়লিং পয়েন্ট থেকে করেছি, ডিপ্রেশন ইন দ্য ফ্রিজিং পয়েন্ট থেকে করেছি, আর একটা অসমোটিক প্রেসার থেকেও করেছি। কিন্তু এটা একটা টিপিক্যাল এক্সাম্পল নিয়ে আমরা করেছি, কিন্তু তোমাকে কিছু কতগুলো টাইপ করতে হবে। অন্তত প্রত্যেকটা টাইপের এ থেকে ওই কলিগেটিভ প্রপার্টি সব মিলিয়ে অন্তত অ্যাটলিস্ট 12 to 15 নিউমেরিক্যাল তোমাকে সলভ করতে হবে। সেটা তুমি যেভাবেই হোক করে আমাকে একটা পাঠাবে, আমি তাহলে জিনিসটা একটুখানি দেখে নিতে পারবো যে তোমাদের প্রোগ্রেসটা কেমন হচ্ছে। ঠিক আছে, অ্যাকর্ডিংলি। আর নেক্সট দিন পজিটিভলি উই উইল স্টার্ট অর্গানিক কেমিস্ট্রি, হ্যালো অ্যালকেন অ্যান্ড হ্যালো অ্যারিন। So now it is better that we have completed at least under class 12, from the class 12, the one chapter solution general physical chemistry. So now we will study one day organic and the other day under general physical chemistry, the solid state. Okay, the first chapter we will start. Is it clear?
Okay, sir.
So we are ending the class today.